Okay, hello, welcome to the Tuesday seminar. Our guest today is Marilyn Latour. I collaborate with her for a decade already. Marilyn grew up in Quebec, Canada, and she studied at the University of Montreal. And there she worked on in her PhD on extreme horizontal branch stars in globular clusters. Sorry. And so globular cluster will be the topic of this talk. And after PhD, she moved to Germany, to Bamberg. She worked on the atmospheres of hot stars. And now she's for a few years in Göttingen. And she works on globular clusters and stellar populations, RLI stars, right?
Little bit of RLI. It was a small project.
So the topic is a stellar census in globular clusters with MUSE. Okay, so welcome.
Yeah. I'm really happy to be here today, and thanks, Farah, for the invitation. And so today I'm going to try to present kind of an overview of what we're doing in the Globular Cluster group in Göttingen. So you will see I will present many different results, and you will see many names there. So there are a lot of master students, PhD students, other postdoc. But I think the core of the group are the names that you see here. So there's Sebastian Kammann, which is in Liverpool now, Timo Leverhusa, and Stefan Dreisler, who are with me in Göttingen. So the outline of the talk, I'll start with a short introduction, a few words on globular clusters, then on MUSE and our survey. And I will explain how we analyze all the data that we have in order to get the results that we're using to do our different science cases. And I will focus on 3 topics today. So I'll present some results on the chemistry of multiple populations in globular cluster, lithium-rich stars, and binaries. And I'll finish with a short conclusion. So globular clusters. There's about 150 known in the Milky Way. In our galaxy, they're all very massive, so 10 to the 5, 10 to the 6 solar mass. And they're also very old. So we're talking about ages between 9 and 13 gigayears. And I think in the last maybe decade or 15 years, our understanding of globular cluster in the Milky Way has changed a little bit because we got some information from their kinematics. So from kinematic of globular clusters and also of stars in the Milky Way from Gaia. So now we know that, for example, many of these clusters have like streams of stars associated with them at the front and at the back, because these clusters are basically losing stars as they orbit around the Milky Way. And we also realized that some clusters are moving in a similar way, so orbiting around the Milky Way in a similar way. And we think that actually they were not all formed in the Milky Way. So some of them were formed in other galaxies that a long time ago merged with the Milky Way, and then their globular clusters were absorbed. So one of the examples that is known is Omega Cen. So Omega Cen is the more massive globular cluster in our galaxy. It's a very complex one, and we think it was the nuclear star cluster of this galaxy that merged with the Milky Way a long time ago. It's called Gaia Enceladus. Maybe you've heard about it. And then we have the Magellanic Clouds. So I'm saying a few words about this because some of the clusters in our survey are located in the Magellanic Clouds. And there the situation is a bit different because we can see much younger clusters in the Magellanic Cloud. So we have clusters that have aged between 5 million years all the way to 10 gigayear. So if I'm talking about globular cluster, I have to show a color magnitude diagram because that's a very important tool to learn things. So first, because the globular clusters, all the stars are at the same distance. So basically their observed magnitude is proportional to the luminosity. So this is what we have here on the y-axis. It's just the luminosity of the stars. And then it's still like a single population. So all the stars have roughly the same age, the same metallicity. And this is why we have these really well-defined sequences here. And so basically this diagram is like a snapshot of what a stellar population looks like at a given age. So the less massive stars will still be on the main sequence, burning hydrogen in the core, and those that are slightly more massive will have already evolved on the red giant branch, and then older ones are found on the horizontal branch, where the stars here, they're burning helium in the core. And one of the important features in the CMD is the turn-up that you see here. So people use the turn-up to have an idea of what is the age of the clusters. So you take an isochrone, which is basically a theoretical model of the stellar population, and then you fit it to these sequences, and that's how you can have an idea of what is the age of the cluster by the mass of the stars and the turn-up. So in the galaxy, the clusters, they're around 10 gigayear. It means that the masses of the stars right now are about 0.8 to 0.9 solar mass there. So they're slightly less massive than the sun. Another important thing in globular cluster is multiple populations. So I said it's kind of a single stellar population, but it's not strictly true. So already when people started to look at spectra of RGB stars in globular cluster and measuring abundances, they realized that some elements will show star-to-star variations. So this is the case, for example, carbon, nitrogen, oxygen, sodium, aluminum, and magnesium. So they have these anti-correlations, which means that if you have a star, for example, that is enriched in carbon, then it will be depleted in sodium. So this is a bit what is shown here. So this is oxygen and sodium. And these are the measurements of the stars in NGC 6752. So you have these changes in elemental abundances. Usually we separate the stars in a cluster in two different populations. So we have these, this first population, or the primordial one, that I will call P1 in the rest of the talk. And these are the stars that have a normal chemistry. So I mean that they have similar abundances to the halo stars in our galaxy. So basically solar scale abundances with some alpha enhancement. And then you have the second population, this P2, that has these anomalous abundances or strange chemistry. So for example, they will be enriched in nitrogen and enriched in sodium, but depleted in carbon and oxygen. So this you can see from spectroscopy. So you measure abundances and then you see which star is enriched or not. But some elements are also producing like strong spectral lines. So for example, the nitrogen and carbon. And this will also affect the photometry of the star. So actually you can already see multiple population in the CMD if you use some specific filters. So, oh wow, we don't see anything there, right, on the screen?
Oh, well, we can see, we know that there's something.
Yeah, okay.
Looks better in the internet.
Okay, well, what you should see here is that the giant branch that is here is really spread out when you use this filter, which is the 275. It's in the near UV. So you should see a widespread and even two sequences. And then I have an example for another globular cluster, which is 1851. Maybe you see here that there's actually two sequences, and if you could see everything, they kind of run parallel to each other. So yeah, so this is how this multiple population, they affect the CMD as well. Was there a question or? Okay. Okay, what do we know about this multiple population? We know that they're essentially almost everywhere in massive cluster. So everything that has a mass above 10 to the 5, so above this line here, will have multiple population, as long as it's older than about 2 gigayear. So everything here is multiple population. And you can have some exception, of course, if you're old enough, but not massive enough, you can still have multiple population, but it's really a widespread phenomenon. But, whoops, sorry. But we don't still know where do they come from. Okay, so the thing is that if you want to try to explain them, there's really a lot of characteristics that you have to explain. This is this list here. So it's not only these abundances, there are other things such as the fact that you, in a cluster, usually you have more stars that belong to P2 than P1, and this fraction scales with the average mass of the cluster. And there's helium also changing, and so there's a lot of things to explain. And people have tried to develop many different models to explain this multiple population, but actually none of them is really able to explain everything. So I think that's one of the reasons why it's so difficult, because you need to fulfill so many constraints. Okay, now I'll move to MUSE. So MUSE, it's the multi-unit spectroscopic explorer that is installed at the VLT. It's actually an integral field spectrograph, which means that you get a data cube. So it means that you have an image, and then for each pixel of the image, you get a spectrum. It actually consists of 24 individual spectrographs, and then the information from this spectrograph is all put back together to make your data cube. It was commissioned in 2014, so it's already 10 years. And the wavelength range is quite large. So we're observing between 4,600 to 9,300 angstrom. But the cost of having such a large spectral range is that the resolution is rather low. So it's 3,000, which in delta lambda is about 2.5 angstrom. The first observing mode that was commissioned with the instrument is this wide field mode. So there you have an image that is a 1x1 arc minute, so it's quite large, with a sampling of 0.2 arc second per pixel. And because MUSE is installed at the UT4 of the VLT, this is a telescope that also has the adaptive optic system. So this was commissioned in 2018. And with that was also commissioned the second observing mode of MUSE, which is a narrow field mode. So there you're observing a much smaller field of view. So 7.5 by 7.5 arc second. But you have a really good sampling. So we're talking about 0.025 arc second per pixel. And here you have these three images. So this is 1 arc second. So it's a part of a globular cluster as seen in the wide field mode. So you see all the pixels, but you still see stars. This is the same area with the narrow field mode, so many more stars. And the resolution, the spatial resolution, is actually similar to HSC. So this is an HSC image here. This narrow field mode, we don't use so much in our survey just because the field of view is so small and it doesn't provide the spectra of so many individual stars. But we have some of these observations. The survey. Okay, so this data was obtained from the guaranteed time observing. So this is because the University of Göttingen was involved in building the instrument. So we had data from 2014 to 2022. And we observed in total 26 galactic globular clusters and 8 in the Magellan Cloud. So for each of these clusters, we have different pointings. It's between 1 and 10. And here you have, this is most of the galactic globular clusters. So some of them have more pointings because they're much larger, like 47 Park and Omega Cen. And as you can see here, we're focusing on the central region of the cluster. So it's really the core, the center of each cluster. For each of the cluster, we have at least 3 epochs per pointing. And in some cluster, we wanted to do like binary survey. So we have 5 clusters, so which we have more than 10 epochs, that we can collect a lot of radial velocities and eventually look for binaries. So finally, in total, what we have is we have multiple spectra for more than 10,000 stars in each globular cluster. So that's really a lot of data. Now, how do we analyze that? So I'm going to skip the part on data reduction because this is done with the ESO pipeline, and I really don't know much about it. But what is important for our science case is the fact that we are looking at crowded fields. So we need to be able to extract the spectra of all these different stars that are sometimes blended together. So for that, we use MUSE, which was a program written by Sebastian Kaman, especially for this. And the first thing what MUSE needs is an astrometric and photometric catalog. So we need to tell the program at this coordinate, you're going to find a star that is that bright. And these catalogs we have from HST observations. And then once the program knows which star to expect at which location, then it can extract the spectra and actually also disentangle them. So here we have an example. There's actually two stars here with the red and the green cross. And at the bottom are the two spectra that we're able to retrieve. So we see that these stars, they have different spectral types. So the red one is the red giant with the calcium triplet. At the bottom, we have a star that is much hotter with the passion lines there. So it was probably on the horizontal branch. Once we have the spectra, we need to get the information on the star. So for that, we do a spectral fitting. We use the Göttingen spectral library of model atmosphere. It was also computed for this project. It's using the Phoenix code. These are LTE models, but they assume the spherical symmetry, which is important for the red giant stars because they're very large. And the parameter range is quite large because we have many different stars in the clusters. And besides the range in effective temperature and surface gravity, we also have different metallicities and different alpha enhancement. And these models are public. They've been used a lot actually for all different sorts of purpose. And the first parameter that we get is actually the surface gravity. And this is not from the spectra because they're not really sensitive to surface gravity. So for that, we use the color magnitude diagram and we fit isochrones. So we find an isochrone, like the thing in red here, and that matches well the CMD. So with the right age and the right metallicity. And then from the position of the star, we just find the nearest point on the isochrone and then we know the surface gravity. In the next step, this is where we actually do the spectral fit. And we fit the spectra at once, and the parameters that we optimize, so that we obtain in the end, are the effective temperature of the star, the metallicity, the radial velocity, and we can also include some line broadening, although most of the time we don't, but there was one science case where we needed line broadening. We also fit the telluric absorption, the continuum, but we don't get much information from that. So now we have the information we need. This is almost a summary of all the science cases that we've been looking at. I think they can be divided into two main categories. So there's everything that we can do with radial velocities. This is essentially looking at the kinematics and the binaries. And all the rest has to do with chemistry or stellar parameters. So I could not give an overview of everything, so I picked some topic. So I'm going to talk about these ones here. So binaries, as I said at the beginning, chemistry of multiple populations and the lithium rich. And we're going to start with the multiple population chemistry. So I'm talking about multiple population again. I need to introduce a special diagram that we call chromosome maps. So this is based on photometry, and this is actually how we can separate the star into their different population. So this map, they are based on 4 specific HST filters that are listed here. And on that, we were really lucky because back in 2017, there was a survey for which they published their catalog, and they actually, the people they observed almost 60 globular clusters in these 4 filters with HST, and they made all their catalog public. So we were able to get this photometry to separate the stars into different populations. So I'm going to show you how it works. So you make these 2 CMD. So this one here has the near UV filter. And this is not exactly a color at the bottom, but it's a combination of these 3 colors. It still looks like a CMD, but it looks a bit more funny. And then you select your RGB stars, and you draw this ridge line here. So there's the blue line, the red line, and you do the same here. And then for each star, for each of the stars, you calculate the distance between these two lines, and then you verticalize everything. So it looks like this. And this will actually give you the X and the Y coordinate to make your chromosome maps. And as you can see with this combination of color, you already see these different sequences in NGC 2808. And the chromosome map, at the end, it looks like this. This is your Y, your X coordinate. And when you do that for like different globular cluster, you always have a similar pattern. So you're gonna have a bunch of stars at the bottom here, and these are gonna be your population 1 stars. And then you have this diagonal sequence of stars on the top, and these are gonna be your population 2 stars. In NGC 2808, it's a bit more complex. So people in the past, they've been separating the population 2 stars into different subgroups, let's say. So it's actually 4 different population groups. And what we wanted to do with this cluster was to look at how the different elements, how they change between the populations. So there was sort of a test case because we know what to expect from literature studies, but we want to see what we can do with MUSE. But with the MUSE spectra, we cannot measure the individual abundances on individual lines because the signal to noise is not good enough and the resolution is too low. So what we decided to do instead was to take all the spectra of the stars in a given population and combine them together, so co-add them. So finally, what we get is kind of a representative spectra for each population, but this is going to have a very high signal to noise because we have so many stars. And this is what it looks like. So on the top here, this is the spectra for these 4 populations, and you see really well the oxygen and the aluminium line changing. And then when you plot the residual, you have this anti-correlation. It's very nice to see. At the bottom, it's a different spectral range in which we have aluminium here and magnesium here. You see the anti-correlation again. And then we wanted to try and put numbers, like by how much is the abundance changing. So we did some model to estimate. So we did some model representative of the population, then we changed abundance, and we can predict what sort of residual we should get. We have that here. This is for the sodium line, and these are the observations here. Then we can fit the prediction from the model with the observations, and we get these numbers here that we can compare with literature. And in that case, it worked quite well. So here we are back at the CMD, and we see that there is aluminium and sodium increasing in this direction, and for oxygen and magnesium, it's the other way around. So we looked at that in NGC 2808, and then we did the same thing in a different cluster. So this is 1798. It's a cluster that is in the Large Magellanic Cloud. It's much younger. It's only 2 GeA. And in that cluster, there are 2 populations. So we did the same. We combined all the spectra, and we found some differences in the sodium line here. This is the black line, which is what is observed, and the color were some models for different abundance. And this was really nice because it was actually the first time that we could say that there is something else than nitrogen that is changing in these young clusters. Because the effect of nitrogen, you can see it from the color magnitude diagram. So people already suspected that nitrogen is changing, but sodium, you really need spectra to measure it. So that's what we were able to do. And we found difference of 0.07 dex. And then I'm going to move on Omega Centauri. So this is this very complex cluster. I said in the introduction that it's probably the nuclear star cluster of Gaia Enceladus. And in this cluster, there's many different populations, and we wanted to look at the metallicity of these populations. So there we actually based our work on the results of Bellini et al. So in 2017, what they did is that they identified 15 different subpopulations based on the CMD, and this was done on the main sequence here. I say 15, but really it's actually 5 main populations, and then each of them is subdivided into 2 or 3 different groups. And from the color of the stars of each of these sequences, they could have an idea also about how the metallicity is changing and also helium. So they could basically like rank them, say one population should have more metal than the other. and this way. So what we wanted to do was to confirm this metallicity ranking and then put numbers on what's the average metallicity of these different populations. So we could do it because they also published, for each star that they had in their sample, they said which population it belongs to. So we simply had to match the catalog with our stars that we have MUSE data for. So this is what we got. We were able to get these mean abundances here and to confirm actually the ranking that was done by Bellini et al. And here all the histogram of this population, and then the metallicity is increasing as you go all the way down. And this was kind of a nice project because it was actually the first time since 2005, so since the work of Piotto et al. In 2005, that someone was actually looking at spectra of main sequence stars in Omega Cen, because these stars, they're so faint. In the last 20 years, nobody even tried to take more spectra of these stars, but I mean, we didn't try either, we just had them because we observed Omega Cen. And another thing we realized also, that was new, that we looked at the two most populated main sequence, the red one and the blue one, and we look at the individual group of stars, and we saw that the behavior is not the same in both cases. So for the red main sequence, all the subgroups have the same average abundance, but for the blue one, it's different. We don't really know why, but I think this information is important because we also are working. I mean, we have a big project going on Omega Cen. And the goal of it would be to actually be able to combine the different population on the red giant branch with those on the main sequence. But it's really difficult because on the CMD, you cannot follow them. So you have like these different sequence on the main sequence on the red giant branch. But then when you go to the turn off, all of them, they kind of mix and then you can't really follow. So maybe with the metallicity, we will have more luck. Final topic on chemistry is about the fact that some clusters might have a population that is enriched in metal. So we call these clusters type 2, and this extra population, I'm going to call it this P3. And they actually form this red giant branch. So at the beginning, I had the CMD of NGC 1851. Maybe you didn't see very well, but it was the cluster that had these two sequences running parallel to each other. And actually these P3 stars, they are here at the bottom. And when you make the chromosome map, they appear on the top right corner there. So they're easy to identify as well. We have a few of these type 2 clusters in our survey, these ones here. And what we know from them from previous work is that they are enhanced in some S-processed elements. So for example, the barium is the most obvious one. The content of C and O altogether is different than that of the other stars, and they also might have different iron abundances. But it's not so clear what of these three things is happening in which cluster. So there's still some discussion, like there were a paper recently accepted on NGC 6388 in which they say, oh, there's not even any iron spread at all in this cluster. So we decided to look at the metallicity of these things. So now I'm going to show you the chromosome map of 5 of these clusters. And each point on the chromosome map is color-coded by its metallicity. So in this work, we were really careful to select for each star the best spectra that were giving us the best metallicity measurement. So each of these stars, for example, its metallicity, it's the average value of at least 3 spectra. So this way we got really, really precise measurements. But still, I think it's not really difficult to convince you that there's something going on with these P3 stars here. They're all more metal rich. And this is very obvious from this. Then if we look, if we look at the metallicity distribution here, this histogram, so this is the P3 population, this is P3. It's very clear from the distribution that it's different, but actually the difference is not that large. It's only 0.07 dex. But we are able to see it very clearly because we have so many stars in each population, so it becomes very obvious. And we have the same for some other clusters, so it's quite, we can also measure these small differences because we have so many stars in there. Now I'm going to move to the topic of lithium-rich stars. So what do we know about lithium? There's no lithium production in low-mass metal core stars. And lithium is a very fragile element. So as soon as it reaches stellar layers that are hotter than 2.5 times 10 to the 6 Kelvin, it's going to be destroyed. And we also know very well how the lithium abundances changes along the different evolutionary stage. So here we have the lithium abundance, the surface gravity. This is actually tracing the different evolutionary phase of the stars. So these are results for NGC 6397. What happens is that on the main sequence and the turnoff, you have a constant lithium abundance. This is called the spike plateau. And then you will have the first dredge up. So there's convection in the star that happens, and then you bring lithium in the interior, and the abundance will decrease until it reaches another plateau on the RGB. So you have constant lithium abundance, but you've lost some during the dredge up. And then you will reach the RGB bump, where you have some other mixing process that will finish to destroy what lithium remains in the star. So this is really well understood, and the vast majority of stars follow this trend, except that sometimes you will have stars that have way more lithium than they should have at their given evolutionary phase. But they are very rare. So at the moment, we know 16 in globular clusters and 34 in the galactic field. Where does this lithium come from? We don't really know. So there are three main hypotheses. One of them is the idea that the star self-enriched itself from lithium. So there is something that is called the Cameron-Fowler mechanism. So actually what happens is that if you're able to produce beryllium-7 somewhere in your star, this beryllium can disintegrate in lithium. But usually when you produce the beryllium-7, you do it at stellar layers that are too hot for lithium. So you need to make this beryllium-7, but at the same time have some mixing or convection mechanism that can bring it into cooler layers so that the lithium can survive. This is known to work very well in intermediate mass AGB stars, but that's not what we have in globular cluster. But there's still the idea that some star, for whatever reason, could have this mechanism and be able to self-enrich even if they have lower mass. The other idea is that you have mass transfer in a binary system. So if your star accrete material that is rich in lithium, so for example, it has an intermediate mass AGB companion that makes some lithium, you take the lithium on the star, then the AGB star evolve, disappear into a white dwarf. So you're left with a star that has more lithium than it should have. So in principle, this would work really well. The only problem is that at the moment, there's only one of these lithium-rich stars that seems to be in a binary system. So it's not so promising. Third possibility is that when your star becomes a red giant, it expands, and then it could engulf some smaller bodies that is enriched in lithium. So for example, a sort of planet or a very low mass brown dwarf. This is more efficient at high metallicity. And yeah, in globular cluster, we're talking about low metallicity objects. So we don't really know. And because we know so few of these stars, it's difficult to constrain them. In MUSE, the lithium line, we don't really see it because it's too weak. And we don't have such a high resolution. So this is what it looks like for a lithium normal star. The line should be here, 6,700 angstrom. But if you have a lithium-rich star, then you're going to see something like this here. So this is why we started a collaboration with Alessio Mucciarelli in Italy. So we came up with the idea that, oh, let's look for these objects in all of your spectra. So that's what he started to do. So the idea is to make a catalog of lithium-rich stars in globular clusters. So we have 26 of them. So people could do follow-up on this. So at the moment, what we have is between 300 and 400 quite good candidates. So we're talking about detection above 5 sigma. And this is among more than 100,000 stars with signal to noise above 30. So now I'm waiting for this final list of candidates, and then we're going to be able to try to look at the properties of these stars. So we're going to have way more than just 16. So then maybe we can learn something about at which evolutionary phase they're found. Maybe they have more companions in globular cluster. I have no idea. So this is an ongoing project, but I'm quite excited about it. Okay, now the last topic, binaries. Here I have to make a disclaimer that I am myself not working on binaries. I can say that almost everybody else in the group is doing binaries but me. But I still wanted to say something because it's a big part of what we're doing, and I think we got quite interesting results. But yeah, please don't ask too detailed questions on that later on. What do we know about binaries in globular clusters? There are not so many, okay? So binary fraction is at the most 20%. But they're still important in globular cluster because they provide energy to the cluster. And for one thing, they prevent the whole cluster to collapse on itself, which is quite important. And they also produce some exotic objects that we find in cluster, like these blue stragglers, cataclysmic variable, X-ray binaries, sub-giants, and maybe a few other things. And in principle, they also provide us a way to detect massive stellar remnants, such as neutron star and black holes, because otherwise, if they're alone, you can't see them, right? We need them to interact with something else. So what we know from binaries in globular cluster, it comes from photometry at the moment. So what people do is that they look at the CMD. So here you have the main sequence. And in most of the cluster, you have also a lot of stars scattering above the main sequence. So this is for 3201. And the idea is that if you have a binary, so at a given color, because you're observing two stars, it will appear to be more bright. So that's why you will have stars above here. So this is basically this binary main sequence. So this method, it's only focused on main sequence binaries. And it's also sensitive to luminous companions. So we're talking about a mass ratio above 0.5, because of course, if you have a white dwarf companion, it's not going to change anything to the luminosity and you're not going to see it. So with MUSE, what we wanted to do, it's actually a spectroscopic binary survey. So because with spectroscopy and radial velocity variation, there you can look for different sort of companions, and you can look at all different evolutionary phases. So for that, we had extensive follow-up, so more than 10 epochs in 6 clusters. So 5 of them are in the galaxy, and we have 1 in the large Magellanic Cloud also. So the idea, basically, it's way more complicated than what I'm going to explain, but it doesn't matter the details. So the idea is to look at how much the radial velocity is changing for each star. And based on that, we can give it a probability of being a binary. So these are 2 extreme examples. If we take the star with the radial velocity in orange here, it's basically not changing. It's constant. It's consistent with constant radial velocity. So this object here will have a very low binary probability. And then if you have another star with such large scatter in radial velocity as the blue one, then this object will have a high probability to be a binary. So here we know that if you have changes in radial velocity, it can be due to something else than binary. So we have, for example, these pulsating stars like the RR Lyrae. They will also change their radial velocity. But these stars in cluster, they are very well known. So we know from the beginning which ones are pulsating, and then we take them away from the survey. So we are saying, okay, we have radial velocity variation in these stars, but it doesn't come from binary. So we were able to do that in 4 clusters at the moment. And this is just to show our sample of stars in omega Cen. So all of the points here are the stars for which we could give a binary probability. So for that, we actually need to have enough measurements. So I say we have 10 more epochs, but sometimes the star is not extracted in all data cube, or it's outside of the field of view. So we make sure that we have more than 5 measurements for each star. And then this is color coded by the binary probability. So the dark ones here are those that are very good binary candidates. There are not so many in omega Cen, so it's a small number, but we find them all across the CMD. So then once we have identified those that are more likely to be variable, we need to try and get the binary fraction. So the first thing is the observed binary fraction. So for example, we can select all the stars that have binary probability above 0.5. Here. But this is what we observe, and we know there are some biases. So for example, if you have a binary with a really long period, then you can't detect it because the period is too long. Or if you have an inclination that is not favorable, then you don't have large amplitude, so you're also gonna miss it. And with our method, we have something with the mass ratio that we cannot detect binaries that are made of two stars of the same mass, because then they will have the same spectra. And because we are at low resolution, we're not going to see these two lines. We're just going to see one spectral line that is kind of getting smeared out and a bit less smeared out. So these we can detect very well. Actually, this is complementary to the photometric method because we are much more sensitive to looking at invisible companions, for example, white dwarf stars. So this process of going from observed binary fraction to corrected binary fraction is very complex, but we do the best we can. And then we can have something like this, for example. This is an NGC 1850. We have 700 binary candidates, these with a high probability. And then once we apply the correction, then we increase a bit the fraction. So this is the observed one for different magnitude once it's corrected. And then in that cluster, in the end, we have a binary fraction of 24%. In 47 TUC and omega Cen, these very massive cluster in the galaxy, we have actually very low binary fraction, so 2%, which is in good agreement with the photometric estimates. And NGC 3201 has a bit more binary, almost 7%, but this cluster is a bit different, so it's not core collapsed, which means that we were kind of expecting more binaries in there because the core is not collapsed, so you need more energy to keep everything there. So then the next thing that we can look at is the binary fraction across the different evolutionary phase. And they are quite consistent, except for the blue stragglers. But this is really something expected because these blue stragglers are actually the product of binary interaction. It's a nice result that we find more binaries in blue stragglers, 10% here and 20% in omega Cen. Then we can also look at the binary that we find in globular cluster with respect to the age of the cluster. Remember, NGC 1850 had 25%, but this is one of the young cluster. And actually what happens when you look at cluster at different ages, you're going to look also at different type of stars. So for example, in the Magellanic Cloud, if you're around 2 giga a year here, but the stars that you're going to have, they're like A, B spectral type, so they're much more massive. So what we're seeing here is actually that with the more massive stars in cluster, we have a higher binary fraction. This is actually following the trend that we see also in the galactic field. So these crosses here, they are the binary fraction for stars in the galactic field of different mass or spectral type. So we have the same thing in clusters, except that the binary fraction is always lower. Okay, now that we have identified our binaries candidate, then the next thing is to try to fit like an orbital solution to it, so that we can learn something about the period, the mass of the companion, and the eccentricity. And this is where we can identify these massive companions like the neutron stars and the black holes. So this is one of these very secure stellar mass black hole candidate in a binary. This is NGC 3201. It's a star that is at the turnoff. And this is the radial velocity curve. It looks funny because the eccentricity is quite high. So this particular system has a period of more than 100 days. And the minimum mass of the companion is 4.3 solar mass. So we're pretty sure this is a black hole there. And this is the second candidate. So this one is less secure. It's a bit more complicated. It's in the LNC. So it's also a turn of star with a black hole companion, but we have a B-type star there. And we're not so sure what is the mass of the B-type star. And then if you're not sure of the mass of the primary, it will affect the minimum mass. But still, it's a very interesting system because it has not only radial velocity variation, but also light curve variation here with the same period of about 5 days. And last thing, I think this was an important result from this whole binary survey, is that we compared also our binary property with what is expected from people that make models of globular clusters. So in the case of 47 Talk, we were collaborating with people doing model of globular clusters. So they basically gave us a model and they say, okay, you can look at what sort of binaries we have in there. And this is what we have here. So this is the period, and this is the number of binary. And this orange curve here is what was predicted from the simulation of 47 Talk. So there were a lot of short period binaries in there. This is period below 5 days, basically. And in blue, what you have here are the periods that we find in the MUSE data. And these short period binaries, they're not there. And actually, they should be easy to detect because the shorter the period, the higher the amplitude you have on your radial velocity variation. So this is not, we made sure that it's not really a sort of bias. So I think if we don't detect them, it's really because they're not there. So right now we're trying to work with people who make model and then try to see, okay, can you come up with some way of having more long period binaries in your globular cluster model, because the short ones don't seem to be there. And this is also true for the other clusters. So to a lesser extent, but the period of the binaries, it's really not peaking at very short periods, it's much longer, like about 100 days. And this was my last slide, so now I'm coming to the conclusion. I hope that I convinced you that we did a lot of stuff with this MUSE data. So to summarize these 3 topics, so in terms of multiple population, we were able to do a lot because we have the photometric information on the stars to be able to separate the population. And this is something that people working with high resolution spectroscopy, they don't always have. Because when you do high resolution spectroscopy, you're looking usually at the outskirts of the cluster because you have less crowding. And these regions are often not covered by HST data. And by combining HST photometry and our spectra, we are able to learn things on the metallicity of this population and also on some elemental abundances when we combine all the spectra together. Lithium-rich stars, it turned out that MUSE is very efficient at finding lithium-rich stars. This came up as a surprise. Nobody really had thought about looking there. So I think it kind of shows that sometimes when you have a lot of data, you don't know ahead everything you're going to do with it. And finally, on binary stars, I think my colleagues, they were a little bit disappointed because they were hoping to find more of these black hole, stellar mass black hole and neutron star companion. So they're still quite rare, but at least we found a few. And yeah, so the properties of the binary seems to be a bit different than what is normally included in this model of globular clusters. So hopefully we can, yeah, maybe help the theoretician to make better models of clusters. So thanks. I'm going to stop here.
Thank you very much. It's an interesting talk. So time for questions. Przemek?
I actually have 2 questions. One, I was wondering whether I can connect these 2 topics you are talking about, binary stars and multiple populations.
So what? Multiple population and
binary stars.
Binary stars, yeah.
So you can expect that your clusters, dynamical interactions between stars, merges significantly than in the field. So could that be an explanation for multiple star populations? Do people think about that?
Yes, one of these possibility is actually, in respect to binaries, actually this idea that in the beginning of the life of the cluster, you have a lot of binaries because you have these very massive stars that are still there, and that these binaries, they can interact and then kind of eject a lot of material that could have like different elemental abundances in them because you have interaction of binary stars and stellar winds and everything. So there is some work in this direction.
And I have another question about Omega Centauri and possible intermediate black hole detected
Yes.
cluster.
Yes.
It was detected based on fast-moving stars and the center of the cluster.
Yes.
Do you have RV velocities for these stars, and do you see any changes?
No, they are too faint. Actually, we're collaborating with the Heidelberg people who made that paper. So they also have, we have MUSE spectra for the same field, but these ones are too fine. They're on the main sequence, but I think they got a James Webb proposal accepted to try and maybe get spectra, better spectra, and get RVs. But yeah, that would be really important.
Okay, next question, Milena.
I also have two questions. One is related to spectroscopic analysis.
Yeah.
So if I understood well, so first you get log G from the isochrones,
Yes.
and you fix it,
Yeah.
and then you do this like analysis, like chemical elements analysis, like atmospheric parameters analysis with a fixed log G,
Yes.
right?
Yes.
And then when you have all the parameters for a given population, you average it, right? I mean, if you want to have like the high signal to noise spectra.
With the high signal to noise spectra, actually, we don't really care about the parameters. So it's just that we take all the spectra of the stars and then we stack them together. But we still then know for each star what is its temperature and its average metallicity. So, and this is important when we do the modeling of the population, for example. But I'm not sure if I got the.
Yeah, well, I was wondering. Okay, so you just take everything, all the spectra from a given population, and just treat it as a like a plot that you average, right? You don't give any additional assumptions.
Well, there's two things. When we go to make. Okay, so when we get this spectra here, we just combine the spectra together for the stars that belong to a population. So it's really just at this point, when we look at this, this is purely qualitative. Okay. So it doesn't matter what are the temperature of the stars. But then when we get the number, this number here, then it becomes important because when I make the model here, I need to say, okay, I know that in population 1, now I don't have the number, but in population 1, I have, let's say, 100 stars, and each of them have different temperature, different log G. So when I make my model for these 100 star, I need to say, okay, I'm going to take one spectra for star number 1 that has these parameters. I'm going to put it there, and then I'm going to add in my model the spectra for each of these stars, taking into account that they have different temperature, different surface gravity.
And rotation as well, because that can.
No, actually, in these old cluster, the stars, they don't rotate very fast. So we assume there's no rotation. Okay. But in the Magellanic Cloud cluster is a bit different. We didn't do. Yeah, I think 2 giga here, it's still not a program rotation, but we have some younger cluster in which then it becomes important, the rotation.
Okay, so just a very short second, if I may. Those candidates for, let's say, compact objects in binaries, are they bright enough to get a better follow-up with spectroscopy, with better resolution spectroscopy, or they are too faint as well?
That's a good question. Let me check here, because I have the CMD of 3201, and it's turnip star. So in principle, it's not so faint. Where's my CMD?
So one is the B stars, quite bright.
This one we have some proposal to try and get follow-up for the one in the Magellanic Cloud, but in 3201 we don't really have any. I mean, you're still at 18th magnitude, so yeah, this is 18 magnitude in V, so it's a bit faint, I think, for resolution spectroscopy in 3201. But the one in the Large Magellanic Cloud, there is some. I think we either propose to get a better spectra. I'm not sure if it's been accepted, but that we tried.
Yeah, because that's pretty common that those may not be compact objects, but some, remnants of evolution of star binary.
Yeah, the thing is that the problem with the one in 1850 is that we think it's a main sequence B star, but it could also be what we call the bloated star. So it's a less massive star, but it has a very puffy envelope. And then if your primary is less massive, then the limit, I mean, the minimum mass for the companion also goes down. So that's the tricky part with these B-type stars. It happens often that you're not super sure if it's really on the main sequence or not.
Another questions? Marcin.
I only like to be sure you at first select photometrically your different populations, and next you for those stars you stack your spectra.
Yes, always. So we always get the population from the photometry first.
Other questions? So I have a question. Can you see differences between the clusters that formed in situ in the Milky Way and that the cluster that arrived?
Not really.
Chemically, nothing.
There has been one paper in which they tried to look for chemical properties. So I think they looked at the chemical abundances of stars in all different clusters, and then they were trying to match them to find like a group of clusters that share properties, but not only for one or two elements, but for all of them. And this way they made a group of stars that was omega Cen, and then a few other clusters that have compatible chemistry pattern. So then their theory is that these clusters, they came together, but the problem is then when you look at the kinematics of these clusters, they're a bit different. So I think people are not really sure if kinematic is really the best way to put together clusters that would come from another galaxy, because depending when the globular cluster was stripped out from its galaxy during the merger, then the kinematic is not affected in the same way. So that's what I remember from reading that paper. So I think there's still some work to be done there.
Okay. No more questions. Okay, so yes, okay.
One question. When we have globular clusters from our galaxy and from, let's say, the Large Magellan Cloud, which one will be the most distant? There are some globulars which belong to our galaxy, which are more far than LHC or.
That's a very good question. I know among the ones we have, I mean, the one we selected for a survey in the Milky Way, we all took them quite close because otherwise we cannot get good data. But I have to say, I'm not really sure. So I know that most of the, so for example,
from your survey, there is
from my survey, they're all closer, the ones from the Milky Way.
Okay, so no more questions? No questions on Zoom? No. Okay, so let's thank Marilyn again.
Okay, so thank you very much. Thank you, Paweł, for leading the seminar. Next week, Anna Dukaras presents BJ will tell us about galaxy clustering. Yeah. So, and notebooks somewhere.